All right, so this video is going to be about Unit 9, and you've got a handout that I think says Unit 9 intro notes at the top, and basically you can just take notes straight from this video onto that handout. So in the first example, we got this table here. The idea is that we're going to be dealing with functions not of one variable anymore, but of two or more. And the vector functions we've been dealing with are really just one variable functions because you can always write them in terms of like t. The x is in terms of t, the y is in terms of t, and the z is in terms of t. So this one, we've got wind chill, w, and it's dependent on two different variables. It's dependent on air temperature t and wind speed v. So really what you might write on the side as w is going to be a function of temperature and wind speed. Okay, so that's kind of a notation that we'll be using more and more. In this problem, it says, estimate the wind chill index if air temperature is 30 degrees and wind speed is 12 miles an hour. Well, here, this whole column right here is when the temperature is 30 degrees. And we need to figure out what's the wind chill, the stuff in the actual, this data here is the actual wind chill. So what we need is to figure out, well, when it's about 12 miles an hour, that's between the 10 and the 15. So the wind chill should be somewhere between 16 and 9, and probably a little closer to the 16 than the 9, because 12 is a little closer to 10 than 15. So what we can do to figure that out is a method called linear interpolation. So use linear interpolation, which basically means assume that that this data, at least for between 10 and 15, and the wind chill is 16 and 9, that's in terms of degrees also, Fahrenheit, that follows a linear pattern just in this region right here. Okay, so we know if T is 30 degrees Fahrenheit, then W, not W. Oh no, yeah, that's right. W is the wind chill. Wind chill 16 when the wind speed is 10. And we also know that W is 9. The wind chill is 9 when the wind speed V is 15. So really what's happening here is we're kind of eliminating one of these variables. We're forcing T into a constant. So then these represent two data points. When V is 10, W is 16. When V is 15, W is 9. So we can actually use these two data points to come up with a linear model for how V and W are related when T is 30 degrees. So assuming assuming a linear relationship between W and V when T equals 30 degrees Fahrenheit, we can use the y minus y1 equals m x minus x1 point slope form. The slope, let's see, we'll work it out over here. Slope is going to be 16 minus 9 over 10 minus 15. So that'll be 7 over negative 5. Okay. So the slope is negative 7 over 5. In this one, our x's are like our v's. So v minus something. And over here it's w minus something. And then I'll pick, I'll pick this point, the 15, 9. So when v is 15, w is 9. Here's a model that we can use. And so now let's plug in v equals 12. So, because that was what we were originally trying to do when wind speed v is 12. So when v equals 12, w is going to be negative 7/5, 12 minus 15, and then if I add the 9 over, that's going to end up being about 13.2 degrees Fahrenheit. And so yeah, it's a little bit closer to the 16 than the 9. Okay. So let's keep going here. Now, in that example, w, we mentioned it's a function of it's a function of two variables, temperature and wind speed. Okay, must have been late when I made this handout. All right, so if you have a function of two variables, a lot of times you'll see f of xy. And then typically that's represented with a z a lot of times. And so what happens is your inputs come from the xy plane. So like you have some point here, xy. And then you plug that into f, some function f, and you end up with a real number. So, you know, here's the z-axis, you end up with some z value right there, which is f of xy. Okay. Sometimes you see it represented a little differently, where the z-axis here is represented, you know, like here's the x and the y-axis, and here's the z-axis, the same way that we've been doing it in class a lot. And so in this case, you have some point in the xy plane, x comma y, and then you plug that into f, and you get some value, and that's kind of like the height there. So this right here is your height, z equals whatever you get when you plug in x comma y. And then this coordinate right here is really x, y, and then whatever you get when you plug those in. So both this side here and this side here are different ways of representing a function of two variables. Okay, if you had three variables, then what you're doing, you can only represent this like one way, really. You start out with a point in 3 space. So you start out with some x, y, z. And then you plug that into f. And you get some point floating around on a new axis, which we'll call w. So typically when you have three variables, you write something like f of x, y, z. So you're plugging in an x, y, and z, and you're getting a single value back, w. Now there's no way to represent this one similar to how we did functions of two variables, because you'd have to start, you'd need a fourth dimension that you could graph, which if you can figure out a way of doing that, awesome, but otherwise I wouldn't bother trying. All right. So on the next page, on your next page, it says the definition of a function for n variables. And the n variables, when you have unknown numbers of variables, not just x, y, z, you typically go x1, x2 up to xn. And it's a rule, a function is a rule that for every set of inputs that you have, you get an output. And it's whatever you get when you plug in x1, x2, dot, 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 up to xn. And you've got a domain that all of these x1, x2, xn's come out of. That's D. And it's going to be a subset of Rn. Okay, it could actually be Rn too, so I suppose we could do that as well with the little equals underneath. Okay. So what this means is typically you've got a function that goes from some domain to just R, right? You get only real numbers, single values back. Oftentimes, the domain is the entire Rn. Sometimes there are no restrictions on your x, y, z, or x1, x2, all the way up to xn. Okay. The range is not always all real numbers. Remember, this is the codomain. The range is going to be the set of all the f values you get when you plug in x1, x2, dot, 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 to xn, such that the inputs come out of, those are elements of the domain. Okay, so let's do some examples with multivariable functions, just so you can get a feel for them. I think they're pretty easy overall. At least the intro stuff is pretty easy. So f of xy equals this thing with x's and y's in it. Find f of 1, 4, f of t squared t, and then find the domain of that. Okay, so let's do f of 1, 4. So that one I'm going to plug in 1 for x and 4 for y. So 3 times 1 squared root 4 minus 1. So that's really 3 times 1 times 2, so 6 minus 1, that's 5. Okay, so that one's done. Let's do f of, what is it, t squared first, then t. So I'm going to replace the x with t squared. So it becomes 3t squared, and then the x is squared. And then root y, which is t, and then minus 1. So that's going to be 3t to the 4th root t minus 1. Okay, the domain of f, let's see, domain of f. Well, there are no real restrictions on x. X can be any real number. But y is stuck underneath a root, so y has to be greater than or equal to 0. And so really, since x can be anything, the only real restrictions are on y. So y is greater than or equal to 0 is our domain. And then when you sketch the domain, remember now, the points where the values you're picking are coming out of the xy plane. So the sketch of the domain, if this is the x-axis, this is the y-axis, is going to be everything on the x-axis and above, right? The red is y is greater than or equal to 0. Make sure that you kind of make that x-axis bold down there, right? Because you want to include that. Otherwise, you put a dotted line on it. So for another sketch the domain type of problem, let's look at this one because this one's a little weirder. ln, the insides of ln, the stuff, the inputs for ln have to be positive. You can't plug in 0 into ln or negatives into ln because remember, ln just looks like that. So the domain has to be, the inside of ln has to be positive. So x squared minus y has to be greater than 0. So if we do a little rearranging, x squared has to be greater than y. Some people prefer seeing it this way, y has to be less than x squared. So if we sketch that graph, y equals x squared is the parabola. This is not including x squared. Instead, it's everything below x squared, all the y values that are underneath the parabola. So that's this region down here. Y is less than x squared. And that's the domain. So really, any point that falls into that blue region, you're allowed to plug into here. Any point that doesn't fall into that blue region, then you're going to get undefined. And any point that falls on that parabola itself, you're going to get undefined. Remember, if you're not sure which side to shade, just pick a test point that's really obvious. You know, pick like -4 or 0, -4, plug it in and see if it works. And if it works, then you shade that side. If it doesn't work, you shade the other side. Okay. Example 4. Find and describe the domain of f. And f is a function of 3 variables. So, let's see. We know that the inside here has to be, since it's a square root, the inside has to be greater than or equal to 0. So if I bring the 1, or let's bring the x squared, y squared, and z squared over. So 1 has to be greater than or equal to x squared plus y squared plus z squared. And if I rearrange that just so that the variables are in front, it's less than or equal to 1. Well, if it equaled 1, that'd be a sphere centered at the origin with radius 1. So less than that is everything inside the sphere. So this, it can be described, this is the domain. This is the domain, by the way. The domain is all the points on or within a sphere of radius 1 centered at 0, 0, 0. Okay? Hopefully that makes sense. In fact, one thing that we'll move into is something called level curves, or level surfaces. And really what that means is when you set this equal to various constants, what do you get? And so really this one, you're going to get a bunch of different kinds of, you're going to get like layers to an onion, essentially. So you're going to get these concentric spheres in there. Okay. Let's see, what's next? Okay, describe the graphs. All right, so okay, so the first one, this one, we'll replace these with z's. So think of that as z equals 1 minus x minus half y. If I get all the variables on one side, well, this is ax plus by plus cz equals a constant. That's the equation of a plane. And the plane has a normal vector, which we can get straight out of the equation. It's got the normal vector, or one normal vector is 1, 1/2, 1, right? That's from the coefficients here. And it contains, because really to define a plane, you need a normal vector and one point in the plane. So it contains the point, I don't know, what's an easy one? If x is 0 and y is 0, z has to be 1. So the key here, find an easy point. Okay. Let's look at B. So in B, we've got z equals root 1 minus x squared minus y squared. And if you're not sure just off the top of your head what that is, let's square both sides. And then bring all the variables to one side. So we get x squared plus y squared plus z squared equals 1. And this right here is a sphere of radius 1, centered at the origin. Okay, so if I just graphed it right now, it would look like this, right? That, but the original function is really just the positive root of that, right? Z is just the positive part. So f of xy is only the top half, the top hemisphere, let's say. And it can equal 0 as well, so you also include that circle in the xy plane. So I'll write here, including circle in the xy plane. So I'll highlight that part. It's this part here, right? It's the top half of that sphere, including this part here. Okay. All right, let's look at the next one. So negative root x squared plus y squared. So I'll call that z again. Z equals negative root x squared plus y squared. And if you're not sure what that is, then square both sides. And the negative goes away. Well, this right here is a circular cone. So that's this shape here. I'll do this one in black. Like that. Okay, but we've got another but here. F is only the negative root, right? So f of xy is only the bottom. By the way, when you have a double cone like this, each part of it, each chunk is called a nap. So it's or nape, maybe, I'm not sure. But it's the bottom nap or nape of the cone. So the only part that you want is this part, not this part up here. Okay. So now we've got this thing called level curves, or they're also called contour curves, or contour plots, or contour maps. There's a whole bunch of different names for basically the same idea. And those are kind of like, what's it called? Like the topological maps that you see sometimes that show like elevations of mountains and things like that. So I just showed you a couple diagrams. The actual level curves are these guys down here, or in this case, it's the stuff that's up above the picture here. And the idea is that you essentially slice whatever 3D shape you have, and you take and you take that cross section that you get, and so like this circle that's going around in that area right there, that ends up becoming, you basically just project it right onto the xy plane, and you get this circle down here. And so in this one, I can't really read the x. I think this is when z equals 6. So what you would say down here is this is the level curve or the contour curve, you know, for z equals 6. And for some reason, a lot of times the textbooks switch out z when they're talking about level curves with the k. I'm not quite sure the reasoning behind that, but that's very common. Okay. And a lot of times you see that the level curves are evenly spaced. So like you might do it at 1, 2, 3, 4, 5, 6. So you might do it at 2, 4, 6. And that gives people a pretty good idea of like, you know, how the elevation changes as they're walking along, and or like picturing things on a map. Okay, so example 6, we're going to sketch the contour map of f of xy equals 4x squared plus y squared for various values of k. So first, let's think of this. This is really like z equals 4x squared plus y squared. That's actually going to be a elliptical paraboloid. Elliptical paraboloid. So it does something like this, right? Where you get parabolas going in this direction and this direction as the thing gets higher and higher up. So you got parabolas going in the the xz plane and the yz planes, or planes parallel to those. So like parabola here, parabola there, all that kind of stuff. Okay, and then you've got parabolas coming towards you and parabolas going behind as well. But basically, there's the shape. And so the idea is that we want to figure, okay, when k is 0, that's actually the bottom right here. You're gonna get a dot there. And then we're gonna look at, well, when k is 2, so really when z is 2, you know, you're gonna get a different ellipse. And when z is 4, you're gonna get another ellipse. And when what's slightly bigger, and when z is 6, you're gonna get another ellipse up here. And then the idea is that we're gonna plot all those on the same set of axes, just the x and y axes. So I'll put that over here. X, y. And really the way to do it is, well, just plug these guys in for z. So if k equals 0, then we get 0 equals 4x squared plus y squared. Well, the only time that happens is when x and y are both 0. So our first level curve is just the origin right here. And so what you would write is, next to it is k equals 0. Right, so that you know which one that goes with. Okay, if k equals 2, then we're going to get 2 equals 4x squared plus y squared. And if you rearrange a little bit to get it into a form that we've used in class, you can end up with 1 equals 2x squared plus y over 2 squared. And then you could turn that into 1 equals x over 1 over root 2 all squared plus y over 2 squared. And that's an ellipse, and we would go to the left and right by 1 over root 2. So let's see, I'll use a different color for this. So let's say 1 over root 2 is about here. 1 over root 2, by the way, is about 0.707, I think. And we're going up and down 2. So maybe like here, 2, and 2, negative 2. And so here's the ellipse that we're getting in the xy plane. Okay. If k equals 4, then what do we get? 4 equals 4x squared plus y squared. So if I divide by 4, then we get x squared over 1 plus y over 2. Oh, sorry, this isn't 2. This is root 2 up here. My bad. I apologize. Forgot that I was squaring the thing. So y over root 2. So actually, instead of 2, let me redo this. It's going to be root 2. I don't know why I erased the entire thing, because I could have just changed that. So here we go. Okay, now going back to this. That's squared. Okay, so then this would be out 1 in each direction. So that's not too much past 0.707, so about here. So there, so this is 1 and 1. And then we're going up to 2, 1.4. Let's say 2 is about here. Ugh, undo. 2, -2. So here's that ellipse. So something like that. Okay. And so this one was k equals, what was that, 4? I forgot the k equals 2. Okay, and k equals 6. So if k equals 6, I'll just tell you. Then we get 1 equals x over root 3 over 2 all squared plus y over root 6 squared. So you'd be going out root 6 in each direction on the y's, which is more than 2, but not by much. So maybe about here. So root 6, negative root 6, and then like root 3 over 2, negative root 3 over 2. So there it is. So this one would be k equals 6. And what happens is the further out you go for k, the closer those ellipses get to each other. So they actually get denser and denser, because what happens is this gets steeper and steeper as you're going along. So the circles get bigger, but at a slower rate. So yeah. Okay. Let's go on. So last problem, describe the level surfaces of that 3D, or that 3 variable function. So this is actually a 4D graph if you graphed w equals z squared minus x squared minus y squared. So it turns out if you set, in this case, instead of setting z to stuff, you're setting w to specific values. So I'm going to pick a w that's less than 0, a w that equals 0, and a w that's greater than 0. And I'm actually just going to do these general cases. So we'll look at those 3 cases. Okay, and really w is k. So let's do this. If k is less than 0, k is 0, k is greater than 0. Okay. So if you set w equal to a specific constant k, then you're going to get 3D shapes. So the idea of this whole function is that you get kind of, it's almost like a 3D shape that's changing depending on what you're plugging in. So let's look at what happens. If k is less than 0, then we get x squared minus y squared, or plus y squared minus z squared equals whatever the absolute value of k is. You can kind of think about that a little bit if you want to. Basically, you plug in the k here, and then multiply both sides by -1. Okay. So this right here, if you divide by absolute value of k, you get x squared over absolute value of k plus y squared over absolute value of k minus z squared over absolute value of k equals 1. That's the equation of a hyperboloid of one sheet centered at 0, 0, 0. And it's actually centered around the z-axis too. Okay, and hyperboloids of one sheet, remember, look like this. Kind of like the nuclear power plant type shape. Okay. In fact, that is, nuclear power plants are hyperboloids. All right. If k equals 0, then we get x squared plus y squared equals z squared. And you can work that out a little bit if you don't trust me on that, but I'm pretty sure I'm right. That's going to be a double cone centered at 0, 0, 0 and the z-axis. So that's going to be this sort of shape. And then if k is greater than 0, then we get, if I divide both sides by k, you're going to get z squared over k minus x squared over k minus y squared over k equals 1. And that's going to be a hyperboloid of 2 sheets. And same thing, centered. Actually, I'm just going to do this. Copy. Paste. There. I don't have to write it, although by then I could have written it anyway. So hyperboloid at 2 sheets is this shape right here. So it turns out if you were to graph all 3 of these together, that's awfully big. Well, this is going to be a quick sketch. So the k is less than 0 is the hyperboloid of 1 sheet. So that would be something like this. So here's k is less than 0. And then when k equals 0, that's where we got that double cone. So k equals 0 would look something like, whoops, gotta go through the origin. Would look something like this. And then k is less than 0 is the hyperboloid of 2 sheets. So something like that. This one would be k is greater than 0. So you can almost tell as k changes what's happening to this shape here. It's kind of like if you think of the, I don't know, think of this as time, then you can sort of see, depending on the time, what happens to this shape. It's sort of as time increases, it goes from this hyperboloid and narrows down to the blue cones, and then it sort of breaks apart into those like they're sort of like thimble shapes or cup shapes, right? And so you could keep going with that, and then those things would change a little bit too. They'd stay hyperboloids of 2 sheets, but you kind of get to see how those would change as well. So maybe those of you with Mathematica would enjoy playing around with this a little and give us a demo at some point. All right, so that's the end of the Chapter 9 intro notes, or Unit 9 intro notes, which should be enough to get you through numbers, I think it's 1 through 10 on the 9.1 handout. All right, and I'll see you guys Monday.